Hi, this is Mr. King. In this lesson, we're going to look at the vertex form of quadratic functions. We'll learn how quadratic functions can be graphed from this new form known as the vertex form. But before we do that, we're going to start by looking at y equals f of x equals x squared. Y equals x squared is known as the parent function of all parabolas. For fun, I sometimes call it the mother of all parabolas. So fundamentally, y equals x squared is a squaring function because whatever x is, y will be the square of x. Let's take a look at the table. The easiest value to check for the y value is when x is 0. And if x is 0, we square 0 and we get 0. If we square 1, we get 1 squared, which is 1. If we square 2, we get 2 squared, which is 4. If we square 3, 3 squared is 9. Now the squaring function only puts out non-negative y values. Why is that? Because a squared number, when we square a number, whether it's positive or negative, we get a positive, or at the very least, 0. So we say, when we square a number, we get a non-negative value. So negative 1 squared is the same value as 1 squared. It's 1. Negative 2 squared is 4, and negative 3 squared is 9. And so we can quickly populate an xy table with x values and their corresponding y values. Now each of these represents an ordered pair, and we can graph all of these and we can see what this graph looks like. Let's start with 0, 0. 0, 0 is right here, the center of the grid. X-axis over here, y-axis over here. 0, 0, 1, 1, and 1, 1, we go over 1 to here, and then up 1, which is over here, and so that dot's right here. This grid has increments of 1/2, or 0.5, down the x-axis, and up the y-axis or down the y-axis. 2 goes with 4, right over here. And 3 goes with 9, and that puts that right up here. Now if we go to negative 1, go back 1 on the x-axis, and we go up 1 on the y-axis, we're right here. Back 2 to negative 2, and up 4 over here. And then back 3 to negative 3, and then up to 9, which is over here. Now we can start to see the shape of this curve. And I'm going to fill in these points. Fill in the curve now. So I'm going to try and sketch this, sketch up. Just use those points to guide my pen, like that. I put an arrow on the end because this goes on forever. This is a quick hand sketch with 7 points that are exactly accurate. And it can come up like this. And this is y equals x squared. Now one thing that we quickly notice about this graph is that it looks like it has symmetry to it, vertical symmetry. In fact, if I were to just draw this dark green line down the middle, we see that what we have on this side looks like a mirror image of what's on this side. So it's as if that green vertical line, it's like it's a mirror, and if you look into the mirror this way from the right, you see the opposite. And this is symmetry. This axis of symmetry is a vertical line, and on this line, this is where x is 0. Axis. If we go back to our table over here, we notice that the smallest y value is 0, and it's when x is 0, and that point is known as the vertex. The vertex has coordinates 0, 0. I'm going to come over here to this question I've written. How does the parabola grow as we move to the left or right of the vertex? So what I mean by that is this. And I'm going to just see if I can zoom our view in here a little bit. There we go. So we can see this better. So what I'm talking about is this. If we start over here at the vertex and we move to the right, move right by 1. So we take and we go over here to this x value of 1. How far does the graph go up? We go over 1 and we go up 1, don't we? Now if we go to the left by 1, we also go up 1 to get to this point. So we go over 1 to the right or go over 1 to the left, we go up 1 for y equals x squared. If we go over 2 from the vertex to the right, we go up by 4. And if we go over 3, we go up by 9. Now if we go from the vertex again to the left, we go left by 2, we go up by 4. That's the same amount as going to the right by 2. So go to the right by 2 from the vertex, we go up 4. Go to the left by 2, we go up 4. If we go to the left by 3, we go up by 9. And that's exactly what happens if we start from the vertex right over here, and we go to the right by 3. We also go up by 9. We're going to look at an example of the vertex form. It's y equals x minus 3 squared. How will the negative 3 change the graph of x squared? Again, x squared was the mother of all parabolas, the parent function graph, the squaring function. So what does minus 3 do? X minus 3 it's being squared, isn't it? So x minus 3 squared can't be negative. X minus 3 squared is always greater than 0. That's a curious and important aspect to the squaring function again. Let's fill out this table now. If we put 0 in for x, we get negative 3 squared, which means when x is 0, we get 9. And if we put 1 in, we do 1 minus 3. 1 minus 3 is negative 2, and when we square negative 2, we get 4. And if we put 2 in for x, we get 2 minus 3, which is negative 1, and when we square that, we get 1. Hey, that's the same number pattern, isn't it? 1, 4, 9. And then if we put 3 in, this is quite interesting. When we put 3 in, we get 3 minus 3, which is 0, squared, which is 0. These numbers, they're all shifted, aren't they? When 0 was x, x squared, which was y, was 0. And 1 was 1, 1 squared was 1, 2 squared was 4, and 3 squared was 9. The order is reversed, isn't it? Now what happens if we put negative 1 in? I think we can see that this pattern for x minus 3 squared is going this way. We keep squaring a bigger number. 1, 4, 9. I bet 16 is the next number if we put negative 1 in. Well, if you put negative 1 in, and then you subtract 3, that's negative 4 squared. That is 16. These are just the squares of the smallest integers. This will be 25, and this will be 36. Now, I actually didn't make this graph, I didn't make this table have all of the x values that I really wanted. So what I'm going to do is I'm going to just bring in the table over here by hand, and we're going to extend it. So I'm going to say our x values and then our y values. Again, this is for x minus 3 squared. And let's x go to 4 and 5 and 6 and see what we get. Well, if we put 4 in, we'll get 4 minus 3, which is 1 squared, which is 1. And if we put 5 in for x, we get 5 minus 3, which is 2, and 2 squared is 4. 149. It's got to be 149. And if we put 7 in, let's just check it one more time. 7 minus 3 is 4. 4 squared is 16. Aha, it's the same bunch of numbers, isn't it? But it's shifted. And the shift appears to be related to that minus 3, doesn't it? Well, we'll find out. Let's graph it now. Negative 1 goes to 16, and that's right here. 0 goes with 9, and that's right here. 1 goes with 4, it's right here. 2 goes with 1, which is right there. And 3 goes with 0. It's right here. Now it looks like it's swinging down, and maybe that point is the low point. 4 goes with 1. And now do you see it? Do you see how we're starting to see symmetry again? This must be the vertex. That's the low point. That's the vertex. It's also the minimum value, the minimum y value of this parabola. And then 5 goes to 4. It's up here. And then 6 goes with 9. 5 goes with 4. 6 goes with 9 right here. And then 7 goes with 16, which is over here. We see now that, as before with the other example, we do have an axis of symmetry that comes down through the vertex right here. And this time it looks like the axis of symmetry is when x is 3. And so I'm going to write that here, x equals 3. That's a vertical line equation. And the vertex this time occurs right here at 3, 0. You'll notice that the axis of symmetry equation pulls its x value from the x value of the vertex. So if you write a vertex coordinates for a parabola, you can quickly write the equation of the axis of symmetry. Now I'm going to take a second here to see if I can sketch this graph in. Kind of go like this, and I usually just try and graph between a few points at a time and sort of lightly sketch. If I were working on paper, that's what I would do. And it can be easier sometimes if you don't have to curve it too much. And kind of go along. I'm not doing quite as well on this side. Almost looks like I might have made a graphing mistake. Did I? I did make a graphing mistake. I can tell because the right side looks really nice, but do you notice that this point right here, I'm going to highlight it. This point right here is out of place. Because this grid is a little bit unusual, I thought I was at 1, but I actually had graphed an x value of 1/2 with a y value of 4, and that was a mistake. So I'm going to just erase that, and this is one good reason to work with pencil. And it should be 1, which means I'm over here, and then 4 is up here. Now when I bring my pencil back in to sketch, it's going to look nice. In fact, when I was sketching this, my hand was feeling kind of strange, believe it or not, because I couldn't make it curvy enough. And it's because that point was out of place. So now there's x minus 3 squared. This is another parabola graph. And if we go back quickly over here to our first parabola, y equals x squared, you notice that they both have this shape. They both open upwards. We say these are smiling parabolas. They open upwards. They don't have the same shape. They don't have the same axis of symmetry either. Y equals x squared had an axis of symmetry at x equals 0. Now, when we go back to x minus 3 squared, I want you guys to think about this. Do you notice any connection between the axis of symmetry for this parabola, which is x equals 3, and y equals x minus 3 squared? Is it a coincidence that the axis of symmetry is x equals 3 and there's a minus 3 in this function? They're completely dependent upon each other, that they are connected, and we say that the vertex in this case moved from 0, 0. It moved to the right. It moved this way. And that distance was plus 3 to the right. That's what that minus 3 did. X minus 3 moves the graph right by 3. And that's known as a transformation. I usually call that a shift right by 3. So we could say, when we answer how will the -3, the -3, change the graph of x squared, it shifts the graph right by 3. And I'll say shift right by 3.